Initiating recording device. Here it is. Okay. Okay. Oh, what's today? The 5th day of calculus ever. Oh God. Am I going to upload this class? I uploaded first period already. I might upload this class if it's better in some way. In other words, I cover a little more stuff in 50 minutes, maybe.
Hello, I'm here. Of course, you're going to upload this class.
Like, who be the recording that he uses?
The FTP stuff?
Oh, yeah.
Yeah, the video? That's this class.
Oh, I always been used first. I know you said I would feel very upset. Oh, I thought you our class all the time.
No, not yesterday. I think I uploaded first period, and today I already uploaded first period. But I think I'm going to replace it with this period because we're going to be able to go through a couple extra examples. I think.
Let's get to it.
All right, so here we go. There's our topic, definition of continuity, and we're going to be talking about the Minmax theorem and the intermediate value theorem and corollaries thereof. Now, this applies only to continuous functions. So let's talk about what a continuous function is.
Oh, we discussed this yesterday.
Yes, we started talking about it yesterday. Perfect. So, firstly, make this a little bigger. Before we get to that, have I talked about gnawing on your math problems yet? Okay. This is what we're doing here. We gnaw on every problem. Okay. We approach each problem either graphically, or numerically, or analytically, or verbally. Yeah, but verbally doesn't spell gnaw. If you look if you read the introduction in your textbook, they talk about graphical, numerical, analytic, and verbal solutions. So, and that's known as GNAV. But what? GNAV? That doesn't make any sense. So I instead of verbal, I call it wordy. So what you're going to do is sometimes you're going to solve a problem or a piece of a problem just using a graph, or just using a table, or doing a little algebra, but you're usually going to explain in a sentence or two what you did. Or you might have a whole combination of all of this stuff in any given problem, okay? So the new component of AP Calculus is graphical numerical. This is older, the algebraic and verbal stuff. But I like to gnaw on my problems, okay? So that's what we're going to be doing. All right, now, here's the definition of continuity. Now, I don't usually write this stuff up ahead of time. It's in your book. I'll probably refer you to a certain page or something in the future. But I happen to have this written out for some reason. I don't know why. But here's the definition of continuity. And this has to do with the graphs we were talking about yesterday, especially the what do you call it? The piecewise defined one?
Yes, you said that the limit exists and it's equal to the function.
Exactly. That's exactly what it says. Continuity at a point such that x equals c for all real numbers. What? Do you know how to read this stuff? No. This is a such that. This is shorthand for such that. This is shorthand for all. It's just an upside down A. Okay, for all. So we're defining continuity at a point such that x equals c, or at a point x equals c, for all x, a member of the real number set. That's just a fancy R.
Yeah.
Okay, and that's the element symbol, element of. So this x is an element of that set. All right, so f of x is continuous at a point where x equals c if and only if. This is shorthand for if and only if. You don't have to write this down. It's on the FTP site. It's in the textbook. This file, see this file? Theorems. Doc, I guess. Theorems is on the FTP site. Okay. So there are three criteria. There must exist a value for f of c. I'm testing for continuity at a point at x equals c, right? So f of c has to exist. That's what this symbol means. Has to exist, or there exists. Okay? Do you see what that is? It's a backwards E. Have you encountered these symbols before? You act like you've never seen these symbols. So this means for each, or there must exist. This means for all. Okay, so there must exist a function value f of c, and there must exist a limit for the function as x approaches c, and that limit and that function value have to be equal, have to match. And then we see that yesterday. Sometimes the limit from the left was the same as the limit from the right, so the limit existed, but the function was defined somewhere else. That would be discontinuous, right? Okay, so we need to know what continuity means. There it is. And then as a consequence of a function being continuous, you can apply the Minmax theorem. Whoops, I went too far. Here's the Minmax theorem. Again, this is all in the textbook. Read chapter 2. Or the pages before the homework page. Let's put it that way. Tonight. All right, Minmax theorem or the closed interval test. Okay, if f is continuous at every point on a closed interval from A to B, then f takes on both a max, let's call it big M, and the min, let's call it little m, somewhere on that interval. For example, kindly consider the following function. Again, you don't have to write this down. It's on the FTP site. It's in the book. Okay, I'm not going to wait for you guys to copy this stuff down. Okay, I'm sorry, we don't have a lot of time. All right, so kindly consider the following function. Y equals 5x cubed minus 5x. Now, can you graph that without a how? Do you really need a TI graphing calculator? Or how would you go about graphing this by hand? How about that? Any ideas? Where would you start? You can factor it. Why is that helpful? Because then you can set it equal to 0 and find the roots. Okay, so in other words, you would get x-intercepts. That's a good thing to do. All right, how would you factor it? First step? Greatest common factor of 5x comes out. What's left behind? X squared minus 1. And can you factor that more? Okay, x plus 1 times x minus 1. So what this allows me to do is answer this question. When is y 0? In other words, what x values have y equal to 0? In other words, where do you hit the x-axis? What are the roots? What are the x-intercepts? Well, that means 5x equals 0, or x plus 1 equals 0, or x minus 1 equals 0. So, x is what? There you go. So those are the x values when y is 0. So those are the intercepts, the x-intercepts. That's when x is 0, y is 0. When x is negative 1, y is 0. When x is positive 1, y is 0. Those are points on the curve. That helps. Okay, let's ask the question backwards. If y is 0, that's x. But what if x is 0? What if you plug in x is 0? What do you get for y? Just plug in x equals 0. What do you get? 0. So guess what? That's also a y-intercept. When you plug in x is 0, you're going to get y is 0. This counts as both an x and y-intercept. Now, this is a cubic equation, yes? Don't you know the shape of most cubic functions? They have like a weird S shape, right? Okay. So if you know the intercepts and you know the shape, you should be able to graph it very easily. By the way, this hints at the fundamental theorem of algebra, you know. Since I have a third-degree equation here, I expected 3 distinct real roots. Okay, that's the fundamental theorem of algebra. Whatever degree the equation is that you're finding zeros for, it could be 4th degree. You will have at most 4 different real roots then. Okay? But they don't have to be real. Sometimes you get complex. They don't have to be distinct. They don't have to be different. Sometimes you get repeated roots. What if this factored out x plus 1, x plus 1? Then you get negative 1 twice. Right? That can happen. But the fundamental theorem of algebra says, since a 4th degree will factor with 4 roots and so forth, whatever the degree is, that's how many real roots, distinct real roots, you can expect at most. By the way, we've covered all the fundamental theorems. Have you realized this? What's the fundamental theorem of arithmetic? When you take a dividend, which is an integer, and you divide it by a divisor, which is an integer, what do you get? You get a quotient, which is an integer, and the remainder, which is an integer. It might be 0. Didn't we use that when we were doing long division? Okay. What's the fundamental theorem of algebra? Here it is, what we just said. What's the fundamental theorem of trig? If you understand the relationship between the Pythagorean theorem, a squared plus b squared equals c squared, and the statement, sine squared theta plus cosine squared theta equals what? What's sine squared theta plus cosine squared theta? 1. Everything comes from that. Everything in trig comes out of that. Everything. All right, so now what we're leading up to is a fundamental theorem of calculus. We're not ready for that yet. We'll get there. Okay, so let's graph this thing. Here we go. Here's my window. All right, so here's my y-axis. No, that's not a y-axis. Here's my y-axis. Should be vertical, and it's still not vertical, but whatever. Here's my x-axis. Label it. Here's the origin. So we had a 0 at negative 1, we had a 0 at positive 1, and we had a 0 at 0. So it goes through these 3 points. Now, be careful. Either it goes like this, then you say that S-curve, or it goes like this. It could go like this. Which way is it? How do you know? There's only 2 possibilities. But what if we plug in the value here, figure out if it's positive or negative? Plug in the half. Okay, go back. What's a half cubed? A half times a half times a half is 1 over 8, right? 1 over 8. So I got 5/8 minus 5 halves. Is that positive or negative? Because I plugged in 1 half. It's negative, right? Okay, right? 5/8 is like 0.625, and 5 halves is 2.5. So that's too big, right? So that's negative. So it's got to go this way because when we plugged in a half, we got a negative. All right, so I'm just going to sketch it. Now you can use HAL to check, but it's something like this. I don't. I'm not specifying a Y scale. I don't know the max or the min. But there's got to be a min here and there's got to be a max here, right? Okay. So Y equals 5x cubed minus 5x. That's a complete sketch except for the max and min. That's sort of incomplete, but all right. So look what the statement of the theorem said. And what's it now? If f is continuous at every point on the closed interval from A to B, then f takes on both a max and a min somewhere in there. Okay. Well, yeah. If you're talking about the closed interval, I'm not talking about every single real number x. I'm talking about a closed interval, say from -1 to 1. Isn't there a max? Isn't there a min? Now, usually you look for mins and maxes where the derivative is... What's the derivative up here? Do you know the first derivative test that shows you where the mins and maxes are? Because the critical points are where the derivative is 0 or undefined, right? Why? Because if the derivative is 0, by the way, derivative is 0 here because you have a horizontal tangent, right? I'm talking top secret stuff we didn't cover yet, right? We're pretending we're starting calculus from scratch, never heard of this stuff, right? But you know that there's a horizontal tangent here, and a horizontal line has a slope of 0, right? So what does the first derivative test say? Where the derivative is 0, you have a critical point where you might have a min or a max because that's where f prime can change sign, does it? Here the slope of the tangent lines are positive or negative? Negative. Here the slope of the tangent lines are positive. So here it's 0. Did it change sign? So it's got to be a min or a max. If it goes from negative to positive, it's got to be a min. If it goes from positive to negative, it's got to be a max, right? Okay, but that's not the theorem I'm talking about. The min-max theorem says you got to have a max and a min somewhere along the line there, but it doesn't necessarily have to be where the first derivative changes sign. All right, let me change that a little bit. What if I made this interval going from 0 to 2? Let's say 2, out here. Now you know what the y values are doing. They're going way up here, right? Let's say this is where you are at x equals 2. That's the y values, right? Okay? Now, on this is a continuous function on this domain, isn't it? There's no holes, there's no vertical asymptotes, nothing weird, right? But I'm talking about the closed interval from 0 to 2. Ignore this. Is there a min in here somewhere? Where? Where it was before, okay. Is there a max in here somewhere? Where? Not where the derivative is 0, what is it? It's at an endpoint, okay? So that's what the closed interval test says. If you're looking for a min or a max on a closed interval for a continuous function, don't just test where f prime changes sign, you also test the endpoints. F of 0, f of 2. In this case, f of 2 would be the max. Okay? That's important. We're going to need that. Sometimes, in the context of the problem, the domain doesn't allow every single real number possible. Maybe it's only good from 0 to 2. On this domain, the max is up here. Let's say you want to maximize revenues, and this is your revenue function. You better use this solution, right? Okay. That's an important result we're going to need, and that only applies to continuous functions. All right. Another result of functions being continuous is this. Take a look at this theorem. The intermediate value theorem. What is this? A where tool? The freak is that? Go away. Okay. A function y equals f of x that is continuous for all x on the closed interval from a to b takes on every value between f of a and f of b. In other words, if y0 is between f of a and f of b, then y0 equals f of c for some value c between a and b. Okay, this is all very fancy gobbledygook, but this is what it means. Kindly consider this function. Right, so I'm going to give you a word problem. Can you find a number that is 1, oh wait, how should I say it? Is the same as 1 minus its cube? Can you find a number that's the same as 1 minus its cube? Now, if you call this number x, didn't that just give you an equation? That's all word problems are, right? They give you words, you make it into an equation. You convert it to math. So, can you write the equation that says the number is 1 less than its cube? How would you write the equation? The number, that's it. I mean, it's not very mysterious. But that's not intuitively obvious that there's such a number, is it? I mean, if I take like the number 2 and I cube it, what? 1 minus 8? That's not going to be 2. How is this going to happen? How could it be that if I plug in a number and cube it, and I subtract it from 1, it's going to be that number? Is there an obvious solution to that? Well, yeah, if you think about fractions. If you put a fraction and you cube it, it gets smaller. You subtract it from 1, you might get the same thing. Oh, okay, so I'm looking for some kind of fraction, or maybe some kind of irrational number less than 1. Okay? How do you solve this equation? I'm going to use the intermediate value theorem to solve it. But what would you do to solve for x? Get all the x's together on one side, set the equation equal to 0 again. Okay, how about if I add x cubed and subtract that, 1, and solve for when it's 0. Now what would be nice is if I could factor that, right? Yeah, I don't know how to factor that. You know the quadratic formula for quadratic equations you can't factor? Right, you know? There is a cubic formula too for depressed cubics. This is a depressed cubic. I could do this with a cubic formula, but I don't remember it offhand. It's very complicated and it involves complex number vectors and crazy stuff. I'm not going to do that. By the way, what's depressing about this cubic? I'll give you a hint. Something's missing. Yeah, when the x squared term is missing, it's a depressed cubic. As it turns out, any cubic equation can be rewritten as a depressed cubic. And any depressed cubic can be solved by Cardan's formula. If you want to look it up later on the internet, be my guest, Cardan with a C. By the way, Cardan had a lot of time on his hands. I think in the 15th century, he had nothing better to do while he was living under the Tower of Pisa. It didn't fall on him, though. You know the Tower of Pisa? It leans. Yeah, he used to live under it. I'm not kidding. And I don't know why he wasn't scared of it, but he did a lot of math while he was under the tower, I guess. Anyway, so let's solve this thing. I can't do this algebraically unless I know Cardan's formula. I can't do it. So what's your fallback position? Realize, by the way, if there is an algebraic solution, like here, this stuff, I want to see the algebra and I want to see the exact answers. Because the only way to get exact answers is by doing the algebra. But there's no algebraic solution to this as far as factoring is concerned. So I want at least a decimal approximation to the answer. What's my fallback position? How can I get it? If you can't do the algebra, you go and ask Hal to do it for you, and Hal will give you a decimal approximation that's pretty darn good. All right, so let's go see Hal. Hi, Hal. Let's solve this graphically, okay? So in y1, I'm going to put this equation, and I'm going to find out when y is 0. In other words, it hits the x-axis. Right? By the way, that's why they call it roots. The roots of the equation, or the x-intercept of the equation, where the curve hits the x-axis. Pretend the x-axis is the ground, and the curve is like a tree rooting into the ground. That's where the concept of roots comes from. All right, so let's write it. X cubed plus x minus 1 equals. And let me start with a zoom 4. And is there such a root? Yeah, it looks like a number less than 1, like we said. Okay, because there's a tick mark here, so that's x equals 1. All right, so how do I get that? Right, F5, You could do it this cycle. I'm going to do f5, root, stuff like that, right? Now, where does the intermediate value theorem comes from? Is this a continuous function? Yes. Notice, some y values are positive. Some y values are negative. The intermediate value theorem says you can get anything in between, namely 0. Okay? Now say that's not what I'm interested in. Wait, say I'm solving this for like 1. When is it 1? Well, there are y values, say 0, and I don't know, 4. Do you have to hit 1 somewhere? A y value of 1? If you hit a y value of 1, is there an x value that's associated with it? That's the intermediate value theorem. But right now what I'm doing is I'm going to see if I can hit 0, and I know I can, right? Because it's continuous, and I have positives, and I have negatives, 0 somewhere in between. That's the intermediate value theorem. Nope. Where did it go? A function y of x that is continuous for all x in a closed interval takes on every value between f of a and f of b. What if f of a is positive and f of b is negative? In other words, if y0 is between f of a and f of b, 0, y of 0 must equal f of c somewhere, and so c is one of the x values. And so you can solve for x. That's what we're saying. All right, so let's do it. Go to f5, go to 0, and the lower bound has to be something negative, and the upper bound has to be something positive, so that we can apply the intermediate value theorem. And there's the answer, 0.682 something. Well, on the AP, if you're rounding off, 3 places is usually enough. So I'm going to change that. I'm going to change my mode from fix 4. What does that mean, fix 4? It rounds off to 4 places for you. But I want to round off to 3, so I'm going to just change that. By the way, do you know what float means? Let's say I just make it float. The calculator will float the decimal place where appropriate. Depending on how many digits it needs in front of the decimal place, it'll put it in the right place, and then it'll give you as many decimal places on the screen after the decimal place as possible. All right? Now you can specify how many you want after the decimal place, but I don't want that. What I want is to round off to 3 places, so I'm going to do fix 3. And do it again. F5, 0, lower bound is negative, any negative will do. Upper bound is positive, any positive will do. And now it's 0.682. So if I go back to my problem, I'm going to state the answer. X is approximately 0.682. What the heck did I write? What's weird here? The dot. Use this on the AP. This means approximated. It's not exact. I rounded it off. Okay? Now, half the AP is like this. You set up the equation you're solving, you write that down, and you write down the solution from how, and you move on. You're done. Unlike the other half of the AP where you have to show all of this work before you can write the answer down. Okay? And by the way, when you do stuff on how, nobody wants to know, oh yeah, I hit F5, then 2, then I did the lower negative, then I did a positive, then I hit enter twice. No, nobody cares. I don't want keystrokes. I don't want to know what your calculator is. I just want to know the setup of the problem and the answer done. Okay? The AP is really 4 parts. Are you ready? Part 1A, multiple choice, no calculator. Part 1B, multiple choice with the calculator. Part 2A, a free response with the calculator, like this. This might be a solution on the free response with the calculator, part of a problem. And part 2B is free response without a calculator. So you really have 4 exams in 3 hours. So it's not 3 hours. It's like, they hand out the exam, they check that you don't have the calculator. They collect the exam, they hand out the next one, they check that you have the calculator. They collect the exam, they hand out the part 2 with the calculator. You still got the calculator, good. They collect that exam, they give you the second part 2, better get rid of that calculator, right? All this administrative stuff adds at least a half hour to an hour. So it could be you're sitting there for 4 hours, guys. Sorry, but that's the way it is. All right, so we just applied the intermediate value theorem to find zeros. That's a perfect example. Sometimes I will be using fix 4 for certain things. Sometimes fix 3, you'll see. All right? Okay, now, you know everything you need to know to actually do a free response question. Here it is. Kindly consider the following. BC, AB2. Sorry, I said it wrong. 76, AB2. Let's see, did I take this exam? No, I took the 79. Sorry. Huh? No, I went to Longwood, in Middle Island, way out east. Well, it's not way out east, but it's more out east than Boulder. All right, so here's a typical free response question. It's only an AB2. It's only the AB exam. We're starting easy, and it's only 2. They get harder when you get to 6 and 7 and whatever. All right. So in those days, by the way, there's no calculator or anything, right? It was just pencil and paper, part 1, part 2. That's it. What? Yeah, they just did it algebraically. There's a lot of stuff you can do analytically. All right. All right. Here's a good example of a continuity question. All right, ready? Here we go. 76 AB 2 says, let h of x. Well, let me read it. Given the two functions f and h, such that f of x is that cubic there, and h of x is a piecewise defined function based on f of x. All right. Now let me write it out. It's f of x, which is x cubed minus 3x squared minus 4x plus 12, that's f of x, over x minus 3, whenever x is not 3, because why? Well, it's not defined there. Otherwise, it's p when x is 3. That, you know what that sounds like to me? It's a hole. We got to fill it. A removal discontinuity. It's a discontinuous function with a little hole in it, right? All right, part A. Find all the zeros of f. How would you find the zeros of f? Not h, but the numerator here. That was f, right? Well, hint, hint, hint.
Give me a long division again.
Hint, hint, hint. This might be one of the factors. You may have an asymptote if this is not a factor. But I'm thinking this might be a factor. So you better do long division. How else are you going to factor this? Unless you have some kind of a hint as to what the factors look like. Now, do you know Descartes' theorem for rational roots? No, really? Oh, gosh. Did you take a pre-calculus class? What the heck do you guys do in 4-H anyway? You party, really? Wow. Okay, Descartes' theorem for rational roots says if a polynomial has rational roots, it will be made up of factors of this coefficient divided by factors of this coefficient. Like 12 over 1, like 4 over 1. There's not too many choices here, right? There's a 1. Like 3 over 1. Look at this. 3 could be a root, so x minus 3 could be a factor. If you said x minus 3 equal to 0, don't you get x equals 3 as a root? Right? Okay, so I'm taking that as a hint. I'm going to divide this out. What is x minus 3? It may not be a good hint. I don't know. What is x minus 3 divided into... Oh, wait, I was in green. I like to keep my problems in color. Sorry. X minus 3 into f of x, which was x cubed minus 3x squared minus 4x minus, plus 12. All right, now remember the fundamental theorem of arithmetic. When a dividend is divided by a divisor, you're going to get a quotient and a remainder. And the remainder might be 0. If the remainder is 0, that means that's a factor, when unevenly, right? Okay, what's x into x cubed? X squared. X squared times x is x cubed. These better match. Sure you messed up. X squared times negative 3x is negative 3x squared. Sorry, x squared times negative 3 is negative 3x squared. Don't forget that we're going to add the opposite or subtract, right? And guess what? All of this cancels, doesn't it? All right, so what are you going to do now? Bring down to negative 4x. But I can't divide a binomial into a monomial, so bring down some more. Okay, how many times does x go into negative 4x? Negative 4 times. Negative 4 times x is negative 4x. And negative 4 times negative 3 is 12. And adding the opposite, guess what? You get no remainder. Okay, so that means that I can rewrite well, let me finish the question. The question was, what are the zeros of the function f of x, right? Okay, so the function f of x was this. And to find the zeros, we can factor it like this. What did we get? X squared minus 4. And you can factor that even more, can't you? X minus 3 times what? x plus 2 times x minus 2. So what are the roots? Well, let's extend this a little bit. X minus 3 equals 0, or x plus 2 equals 0, or x minus 2 equals 0, so minus 2. So x is 3, or x is negative 2, or x is positive 2. Okay? So we answered part A, but part A was a hint that you can rewrite this as x minus 3 times x squared minus 4. What's special about x minus 3 times x squared minus 4 in this case? X minus 3 times x squared minus 4. Why is that good? The x minus 3's cancel. All right, so let's go to part B. Find the values of a value of p so that we have a continuous function h at x equals 3. Okay. So h is now x minus 3 times x squared minus 4 over x minus 3. They cancel. You're just left with x minus 4, x squared minus 4. If x is not 3, and p if x is 3. So in other words, if you graph the original equation, it's going to be a parabola with a hole when x equals 3. And what they're asking you to do is to fill in the hole. That's why it's called a removable discontinuity. You can plug it in, plug in the hole. And how are you going to do it? You're going to use I. By the way, I'm Cuban. I'm allowed to do this. You ever watch I Love Lucy? You know Ricky Ricardo? My dad was just like him. Yes, my dad is a Cuban refugee. I'm not kidding. So I called the continuity definition. I had I. Remember? Where'd it go? Hang on, because of this. Hang on. The definition of continuity. I, right? I can do that because I'm Cuban. Okay, it's allowed. So, first, f of 3 must exist. Can you state f of 3? Look at the function. Well, it's h of 3. Okay, h is the function. Whatever it's called. The function must exist at 3. Does it? Look at this definition. What is it when x is 3? It's p. Okay, fine. The limit as x approaches 3 of h of x must exist. Well, when you're not 3, when you're approaching from the left to the right, you're a parabola. So the limit on the left and the limit on the right have to match. And it's the limit of this thing. And so what is it? Is that a plug-in limit? Remember what I called the plug-in limit? Plug it in. What do you get? Plug in the 3. You get 9 minus 4 is 5. Good. All right. H of 3 has to exist. The limit at 3 has to exist. What? H of 3 has to equal the limit, which means h of 3, p, has to equal the limit, 5. Done. That's why it's 5. You can't just fill it in. You have to justify it using the definition of continuity. You have to write all of that whenever you're justifying continuity. Yes. Yeah, sorry, that's the way it is. Okay. So, wow, we did A, we did B. We're good at this stuff. What about C? Using the value of P, found in part B, in other words, we filled in the hole, and the curve looks like this everywhere now. It's a parabola. Is this an even a function or not? How do you know if you have an even function or not? First period came up with 3 good answers here. 3 good justifications whether this was even or not. When you graph this, what does it look like? All right, so you can look at it graphically. And it looks like this. X squared minus 4 has a root at negative 2, and a root at positive 2, and a y-intercept of negative 4, doesn't it? Okay. So I didn't draw it too good, but is that an even function? Graphically speaking, how do you know? The left side is a reflection of the right side. You have y-axis symmetry. So you can write a sentence that says, yeah, I got y-axis symmetry. Okay, based on the graph. All right. Or, look at the exponents. What degree is this? 2. Is that even or odd? But wait, it has to be a polynomial where all degrees are even. What x? What do you have here? X to the what? If you don't write it, it's x to the what? No, x to the 1 is x. I would have to write it. X to the 0 is 1. So it's like 4 times 1 or 4 times x to the 0. 0 is considered even also. Because it goes 0, 2, 4, 6. 0 is considered even. Okay? So you can say, okay, this is a polynomial where every degree is even. 0 and 2. That makes it an even function also. But here's the definition. If f of negative x equals f of x for all x. Okay? In other words, f of negative 2 is f of positive 2, isn't it? F of negative 1 is, I don't know what it is, but it looks like it's f of positive 1. Can I prove that for every single x that I want to plug in? Not just 2. That only proves it for 2. I want to prove it for every x. Well, remember the function is x squared minus 4 everywhere now, because we plugged in the whole. So I'm going to plug in negative x into x squared minus 4. And I'm going to ask the question, is it the same as just the function itself? Or f of x? When you square it, the negative goes away. So is this side the same as this side for no matter what x you want? That's a question. That's a check. Yes. In other words. Okay? So there's a lot of ways you can justify part C based on then now it's a parabola. Okay, but there you go. Now take a look at the next question. All right, we'll just start it off. You can play with this on your own. 82 AB2 on the next page. All right, let's use this. 82 AB2, next page in the packet, says given f of x as defined there, find the limit as x goes to 0. Okay, what's the limit as x goes to 0 of x cubed minus x over x cubed minus 4x? Well, if you plug in 0, is it a plug-in limit? Can you plug in 0? No, it's undefined. Well, actually, it's not undefined. It's indeterminate. This is a new thing. Have you ever heard of indeterminate? Indeterminate values might actually be undefined, but they don't have to be. One indeterminate form is this. When you plug in 0 on the top, what do you get? If you plug in x at 0 on the top, what do you get? And if you plug in x at 0 on the bottom, what do you get? 0 over 0. And the limit is an indeterminate form. It means it may not be undefined. Is there something you could do to this to make it easier to deal with? Factor out the x. Can't I divide top and bottom by x? Because notice, x is never really 0. It's getting close to 0. I can divide by x. It's not 0. That's allowed. Equals the limit as x approaches 0 of x squared minus 1 over what? All right, now if you plug in 0, is it still 0 over 0? No. What do you get? Negative 1 over, so that's the limit. There's a lot of ways of dealing with indeterminate forms. We're going to revisit this pretty soon with something called L'Hopital's rule. But that is good enough for this question. How would you find the zeros of f? This is f, right? This is a fraction too, by the way. When is a fraction 0? When the numerator is 0. As long as the denominator is in 0 at the same time. Now, we just figured out that when x is 0, the top and the bottom are both 0. That's not a 0 for the function. So when is the numerator 0? Okay, so x cubed minus x equals 0 when? Well, how do you solve this equation? We talked about this. How do you solve an equation like this? What's your favorite F word? 6 letters. Factor it. Take out what? X. What's left? X squared minus 1. Be careful how many letters you use. X times what then? X plus 1, x minus 1. All right, let's cut to the chase because we've got like 3 minutes here. That means x can be 0 or negative 1 or 1. But remember, we're excluding 0 because that gives me 0 over 0, and that's not a 0 of a fraction, right? Okay, so I'm not including that. So what are the zeros of f? Then. Okay, just plus or minus, yeah. X equals plus or minus 1. How about that? The zeros. All right, so the zeros or the x-intercepts. You could write this. Right? Okay. Remember, at 0, it's not an x-intercept because it goes to 1/4. Yeah. Okay. All right, how about this question? Write the equation of the vertical and horizontal tangents. Or asymptotes, sorry. Now, here's your function. When do you get vertical asymptotes in a rational function? When it's undefined. When is the fraction undefined? When the denominator is, so we already solved when the top is 0, now we're going to solve when the bottom is 0. All right, but what I'm getting at is the next part. How do you get the horizontal asymptotes? The horizontal asymptotes are limits at infinity. What does it approach as x gets huge? Can you find this limit for me? What is that limit? This is vertical, right. So notice, this is a vertical line, x equals 0. This is a vertical line, x equals 2. This is a vertical line, x equals negative 2. Again, we're excluding x equals 0 because that's 0 over 0, that's weird. We already took care of that with the limit, right? So that's not part of the answer, this is. You have two vertical asymptotes. But what's this limit? Remember, top heavy, bottom heavy, equal degree, remember? This is what? Which one? Equal degree. So it's 1 over 1. Boom. That's the limit as x goes to infinity. That's a y value. That's a y value. Y equals 1 is the horizontal asymptote. Okay? That's how I get horizontal asymptotes. Limits at infinity. What if we plugged in negative infinity? Would it matter? If we plug in negative infinity, this becomes negative, this becomes negative, this becomes negative, this becomes negative. All the negatives cancel, you get the same thing. So whether you go into plus or minus infinity, you get 1. So that's an asymptote on both sides. All right, so this helps you graph. In fact, that's probably part D is symmetry and part E is graphic based on what you just found. Okay? We're about out of time, so you can play with the rest of this on your own. And that's it for today. Any questions? Okay, hasta la vista.